Hello everyone, welcome to my talk. My name is Charles Wen from National Yangming Jiao Tong University. I'm honored to be here to share our research with you. The topic of today is classifying malicious traffic for IoT network under various encryption schemes on P4. This is done by me and my student, also collaborated with and financially sponsored by Acton Taiwan. So everybody knows that IoT is getting more and more attention. It also brings more and more data volume, so tremendous data, so it's coming. At the same time, cybersecurity is also very important. And that's why there are always new encryption algorithms keep being invented. So in this work, we want to use the P4 to solve the IoT security problem. So everybody here must be aware of the rapid growth of the IoT. According to Finances Online, there will be 25.44 billion of IoT devices connected in 2030. Of course, that brings more and more cyber attacks. For example, Mirai botnet, Verkada hacks, and many others. Traditionally, we rely on the centralized intrusion detection system, aka IDS, to deal with the cyber threats. But facing the tremendous data volume, these centralized IDS can no longer digest such huge amount of the data. Even worse, because of the data privacy, we may apply the different kinds of encryption schemes onto our traffic packets. For example, TLS, SSH, or even for your MQTT packets on the IoT, we encrypt the payload with a specific encryption. But as you know, there are two types of encryption algorithm. One is symmetric, the other is asymmetric. So before we can delve into the packets, we have to figure out which kind of encryption they are applying onto the packets. As a result, we cannot analyze such high-volume encrypted traffic by traditional IDS or deep packet inspection, aka DPI. So how are we going to check malwares in packets? So that's the motivation of this work. Later, we look into the current status of malware classification. We find two recent works, P2SF and the DFR. Both work apply machine learning and deep learning techniques to classify encrypted malicious traffic. But both of them run into two problems. One, they focus a specific type of encryption scheme, such as the TLS. Two, both of them require high computational and storage cost for their AI models. Such two problems motivates to develop a new framework that can be more lightweight and can work under various encryption schemes. So we give you SSPV. SSPV stands for Section Statistical and Packet Variant. How can SSPV solve such two problems? Because we found that in the old time, we always look at the payload and try to figure out which encryption scheme is applied onto the payload. But that's really difficult. So we take an alternative approach in SSPV. We look at the traffic behavior. We found that traffic behavior is useful for classifying the malware. So below are the architecture of SSPV, consisting of four key components. First one, feature extractor. Second, sparse autoencoder. Third, 1D CNN. Fourth, fully connected network. So we will elaborate each component in the following slides. Component 1, feature extractor. According to our observation, we find for each new section, we only need to analyze the first A packets and extract two sets of features from the A packets. There are SS vector and PV matrix. SS vector stands for section statistical vectors that provide the section statistics. Packet variant PV matrix reflect the packet-to-packet difference. So we only need to extract these two sets, then we can conduct the malware classification. Section statistical vector, aka SS vector. We compute 26 features from the first 8 packets. They can be divided into 6 categories of statistical information. There are packet size. We care about their mean, their totals, and their mean and their variance. For the second category, inter-arrival time, IAT, we care about their mean, their total, their mean, max, their connection time, and their round-trip time. The third category, port, we care about the service time of the port. For the category 4, window size, we care about the mean, total, mean, max, and the variance. Similarly, for the category 5, L4 payload size, we care about the mean, total, mean, max, and the variance. For the last category, TCP flags, we care about the number of escape alive, number of escape alive egg, number of escape flood, and number of a reset, and the number of a push. After we collect these 26 features, we combine them into the one vector and send to the next stage. The second feature set is packet variant matrix, aka PV matrix. PV matrix stands for the packet-to-packet difference of the first 8 packets of the session. They can be divided into 4 categories of a packet variant information, and please be aware of that. We care about the direction of this feature, so they are bidirectional. So the first category is packet size. We care about their mean and variance. For the second category, inter-arrival time, IAT, we care about their mean, variance, mean, max, and the total. For the third category, window size, we care about the mean, variance, and the mean. For the last category, flags, we care about the escape alive egg, is sync flood, and is reset. In particular, escape alive and escape alive egg and is sync flood, we don't care about their direction. For the rest of the feature, they are bidirectional. After we collect these 25 features among the 8 packets, we made it into the A by 25 matrix and sent to the next stage. Component 2, SAE for SS vector. Remember that we got the section statistical vectors from the feature extractor. Then we send them to the SPOS autoencoder, or we call it SAE. Why use SAE? Because SAE is more lightweight. As you can see below, we first transpose the SS vector into 26 by 1. And in the latent space, we only use 64 by 1. And then decode the 60 by 1 back to the 26 by 1. So we only take the orange part, use the orange part in the testing. So you can see the very few parameters in the decoder we use to understand the section statistical behavior. Component 3, 1D CNN for PV matrix. In this component, we try to capture packet-to-packet difference by the 1D CNN. Why do you want to use 1D CNN? Because 1D CNN is both temporal and lightweight. You can see below. Original PV matrix is an A by 25 matrix. Then we perform the 1D convolution, it becomes A by 64. And followed by the max pooling, then it becomes a 4 by 64. Then we perform the 1D convolution again, it becomes a 4 by 32. And last, we perform the maximal pooling again, and it becomes the 2 by 32. So it flattens the features from the original PV vector. So it provides a much smaller model size than the LSTM used in the previous works. That also also capture the packet-to-packet difference very well. Component 4, Fully Connected Network, FCN. In this component, outputs from the SAE and 1D-CNN are combined. Remember that we got 64 features from the latent space in the SAE, and we got another 64 latent space from the 1D-CNN, and then we combine them into one 128 by 1 vector. Then we build a fully connected network from this 128 by 1 vector to predict N-type malware types. So in our experiments, the N is 10. So we can build a fully connected network to use the 128 by 1 vector to predict which out of the 10 types of the malware it is of such flow. After introduce the architecture of SSPV, now we'll conduct the evaluation. First, we'll talk about the settings of our evaluation. First of all, we extract the features and run the SAE and 1D-CNN and other components all on the Tofino P4 switch. Of course, we have to do some modification to make sure they can be extracted on the P4 switch. Until an IoT dataset is used, and it includes 10 malware types, including the normal type. And then we also apply the 3 different encryption schemes to the L4 payload. So now the L4 payload will be encrypted by the RSA or the AES or the KPABE. These encryption flows are found in the literature to be used for the IoT application. So after all the encryption are applied, then we send it to the SSPV for classification. Here is the first evaluation result. We compute the weighted average F1 score of a malware classification for each solution. We compare SSPV with the 2 recent frameworks, P2SF and the DFR. Below is the accuracy table of the malware classification under 3 encryption schemes. Let's first look at the P2SF. Under ISA, AES, and the KPABE, the accuracies are 80.95, 81.50, 80.58. So as you can see, the accuracy are not satisfactory. Let's look at the DFR. Under the 3 different encryption schemes, the accuracies are 93.45, 94.94, 76.09. Although DFR can perform well on the ISA and AES, but the performance is not satisfactory under the KPABE. Let's look at the SSPV. The accuracy under ISA, AES, KPABE are 97.54, 98, and 98.19. So you can see the accuracy under the SSPV are all satisfactory. So we can conclude that SSPV is more stable and more accurate than the previous 2 frameworks. Here is the second evaluation result. In particular, we concerned about the computing cost in millions of flops and the storage cost in number of parameters. Let's first look at the computing cost. P2SF consume 21 million flops. DFR consume 14 million flops, and the SSPV only consume 0.069 million of flops. Let's look at the storage cost. P2SF consume 556,000 parameters. DFR consume 109,000 parameters, and SSPV consume only 17,000 parameters. As one can see, compared to the DFR, the better one, SSPV still save 210 times computer cost and 6.3 times storage cost. So that shows the advantages of the SSPV model. Here's our conclusion. For malware classification, we no longer depend on encrypted payload. Instead, we care more about the traffic behaviors. We believe traffic behavior are the key for malware classification. We care about the section statistical and the packet variant features from the first 8 packets of the new flow. And our evaluation result shows that SSPV is more stable and more accurate under different kind of encryption scheme, including RSA, AES, KBABE. We achieve about 98 malware classification accuracy with 0.65 variance. As to the cost, SSPV also improved a lot on the computing and storage costs used by P2SF and DFR. At least we save 200 times on the computing costs and 6.3 times on the storage cost. Remember that all the features and all the SSPV framework can be built on the P4 switch. So I think that's conclude my talk. Thank you for your attention.